When we work with real networks that represent real systems, we're almost always working with a sampled version of the actual system. So whether it's biochemical network or a social graph, typically we do not have all of the information of the original system in the graph. And so that comes about in that we could have either too many or too few nodes. We could be missing edges. We could have edges that don't actually belong in the network. And so we're going to take a moment here in this class to really think about and study how you might think about what that sampling bias might inject into determining statistics about the network. So if I want to know something about the network and I only have a sample, I have to be aware that how I sample it and maybe what the process is that I use to sample the graph, and how that sampling method could inject bias into the measurement that I'm interested in. So we're going to use I'll use a motivating example in this video where we're talking about a crime association network. And so this is a network that has nodes that represent people that are involved in organized crime, and the edges represent some sort of collaboration or interaction between those people in that graph. And so clearly there is a quote-unquote mafia network, and that is the actual population. That's who is associated with who has worked together, and all the people that are in there. At any given time, though, we may not have perfect visibility on that because this is a type of network that wants to stay hidden. And so we could do various versions of law enforcement reconnaissance in order to learn more about the graph and build the graph to help us make decisions about how to deal with the crime and also get statistics to quantify it. But we have to, throughout that whole process, we have to be aware that we don't have the original graph. And so kind of more mathematically, this original graph is we'll call it the population graph, kind of coming from a verbiage of statistics. And then we're going to construct a sample graph, which will use these stars to denote the sample graph, where we don't have perfect information. And so the edge set and the vertex set could be different. And so in particular, the thing that we're going to look at today is to think about quantifying a statistic of the original population graph G. And this could be as easy as average degree. It could be diameter. It could be any number of our statistics that we've decided to study about this graph, anything that we've learned in this class. And so we'll use this Greek letter eta to denote this statistic, and so it's a statistic of the graph G. And so the question is if all we have is this sample graph G star, can we rely on it to give us an estimate that we can trust? And so the quote-unquote plug-in method is simply just to, okay, well, this is what I want, and all I have is G star, so let me just evaluate that statistic on this sample graph G star, and this is my estimate, this eta hat. And so the question is when is this an okay thing to do, and when is it not, and how careful do we need to be? So taking this notion of the statistic being the average degree, so if we have n elements in the actual population graph, so we have n nodes in the original population graph G, then we just take the average over their degrees, and that is the average degree. So if we create a sample, the sample has little n nodes in it, and for simplicity, let's do this without replacement. So that means that we can't pick the same node twice. That our vertex set for the sample essentially are all of these guys, all little n of them, and they have degrees like this. And so then what we're going to do is we're going to compute the plug-in method is just plug in the degrees that we have, k star, and take the average of those over the little n samples that we have. And so the question is, when is this okay? And so we haven't really talked about how we sample. So here we're going to talk about two different ways of sampling. So here, in the first one, in the first case, this Ki star is the actual degree of the node in the original population. So if somehow when we observe that node, when we sample it, we can know how many edges it has. Okay, so that means we actually get to observe every incident edge. Okay, so that's kind of an ideal scenario. So in that case, our estimate of average degree will be exactly, it'll be roughly true in the sense that for everything, those nodes that we've sampled, that we will get an accurate sample of the degrees. Now there could be many nodes that we're going to be missing because we've only sampled little n out of big N. So there's capital N minus little n number of nodes that we're not including in this average. So those could be important. But let's compare that with another sampling method, which is where we only see the degree of the induced graph. All right. So remember, induced graph means that if we have some nodes and we only pick a subset of them, say this one, and this one, then the induced subgraph in that case will be just like this. Will only contain one edge because these other two nodes here and here are not actually in the sample. So necessarily the degree of the induced graph is going to be smaller, which is going to push our estimate of average degree to be much smaller than it actually is. So if we use the plug-in method with this kind of induced sampling, 2.2 here, then that means we're going to greatly underestimate the average degree. So this is just a motivating example where clearly sampling and how that happens is going to make a difference in computing this statistic. So how could we make this better? How could we accommodate for this kind of bias? Then we can update this by saying, okay, the actual degree, so if we're going to use this induced subgraph method, then this K star, what we get in the induced subgraph, is essentially going to be the actual degree multiplied by some fraction, and this fraction represents the fraction of edges that are expected to fall in the sample. And again, that's going to depend on the sampling method. But first of all, we know that this is going to be a fraction, and second of all, this gives us a way of quantifying how the actual degree is going to be related to the sample degree. So in order to kind of do this more formally, we're going to step back away from networks and just think about populations and samples briefly to understand how we might compensate for this kind of sampling bias. So if we have a population, we're going to denote this with this capital U, and it has a whole bunch of values. So eventually you can think about this as being the nodes in the graph, but it just has a bunch of values in the population, and there's capital N of them. Then we can compute, for example, the sum of all of those. Then the sum, we're going to denote that by tau. And we'll call the mean just the total divided by the number. So then if we go ahead and sample these, so if we make a sample, we use capital S for the sample. So in this case, let's assume, again, we're going to be doing this uniformly random sample, but we do have replacement in this case, so we could pick the same node again, just again to make math easy in this case. If this sample includes little n samples, then the sample mean, we'll use this y bar to denote sample mean, and that's just the sum of all these divided by little n. And so the definition of an unbiased estimate is that the sample mean, the expected value of the sample mean, should be equal to the mean of the total population. So again, every time you take a sample, you're going to get a different sample mean. But the idea is that the expected value of that sample mean is equal to the population mean. And that's what we mean by an unbiased estimate. So it means that if there's a statistic that we're interested in, that in expectation, we get that statistic. And we get it with in an unbiased way. So if we wanted to recover the total sum that we had here, then what we would do is we would just, if this is an unbiased estimator, we would just take the sample mean, y bar, and we'd multiply it by capital N. And that would give us an unbiased way of getting at this total. Again, for each individual sample, you wouldn't get the exact tau, but that if you did many of these, the expected value of those would go to tau. Okay, so now we can think about, now that we have this terminology for just populations and samples, one way of accommodating for essentially unbiasing the estimate. So if the estimate is actually is biased, then to unbias it is to divide by this probability pi I, and it is called the inclusion probability. So it's the probability that this element, the ith element, is actually in the sample, and so that is what we're going to use in order to unbias our sample. So if we look at, for example, again here what we're doing is we're taking an estimate of the total sum tau when we have these inclusion probabilities involved. And so we're just taking the sum over the sample, that's the sum over the sample here, of all of these sample points, and we're going to divide by their inclusion probability. And so what we're going to do now is we're going to show that that leads to an unbiased estimate. So what we're going to do is we're going to define this random variable zi that essentially just takes on values 1 or 0. So it's going to be 1 if that ith element is in the sample, and it's going to be 0 otherwise. All right, and we're going to use this to help us go from a sum that's over the sample to a sum that's over the population. All right, so the expected value of this estimate here is going to be the expected value of this quantity, just substituting in this identity. So right now, we're just conjecturing that this is going to work, and what we're going to do is we're going to get down to the end here, and that's going to show us that that's going to be an unbiased estimate. So what we do here is we do this little magic where we use this random variable zi, and that is what's going to essentially do the sampling. It's going to be to decide that if whether I is in the sample or not. And so it's going to be essentially generating these uniformly across all the different options. And so so notice there's no z here, but we introduce this zi here, and so that means that all the elements that are not in the sample, this zi is 0, and so that's why these two equations are the same. So when zi is equal to 1, then that represents all the points that are in the sample, and so that's why these two sums are the same, even though the sum is over something different. And now we can take this expectation into the sum, and so yi is just the values of yi in the population, and pi I is just the population, is the inclusion probability. And so the only random variable is this zi, and so the expected value of zi is essentially the probability that zi is equal to 1, and so that happens essentially pi I times. That's the probability that that element is in the sample. And so that recovers a fraction of pi I. This pi I cancels with this one, and that leaves us with the tau, which is supposed to be the sum over the population, is indeed just the sum over the population. And so that tells us that if we can manage to quantify this pi, this inclusion probability, that will actually give us a way to unbias our estimates. What we're going to find out is in practice, this is tricky. In some specific sampling methods, we can come up with ways of quantifying pi. One of the downsides is that in order to quantify pi, we need to have some information that oftentimes we don't have. However, it does give us a way of understanding the types of biases that different sampling methods will introduce into networks.